So before we jump in, first a quick announcement. The last day of this semester is Monday, so we have our class today. We'll start there actually. We have our class today. We're covering 6.3, checking homework for 6.2. This is the last day of new material for us. The snow day threw things off just a little bit from what's printed up here. Monday the 16th is the last day of the semester, and on that day we're just going to review and have you guys write letters to future 095 students, just like the ones that you read in the Math Studio at the start of this semester. So that's the plan for Monday. And if you are a Math Studio fan, then I want to let you know that the schedule of coverage for the Math Studio changes at the end of the day Monday. So over here in green is the schedule that we've had all semester, and that's valid through Monday. But then starting Tuesday, which is the first day of finals, the schedule changes to the one that's here in yellow. I got an extra copy here, and it's also projected here. So Tuesday, Wednesday, Thursday of next week is different from the usual Tuesday, Wednesday, Thursday Math Studio schedule, okay? So if you need to write down any times, just go to any of the Math Classroom doors or the Math Studio and look for the yellow schedule. Questions on that? Okay, then let's begin here on 251. And at the top, it just starts off with the general stuff about an exam is coming. In our case, it's the final exam that's coming. And there are lots of resources in the usual places for you to practice and prepare for that final exam. In terms of the final exam, our scheduled time is the last day of exam week, which is Friday, December the 20th, 8 a.m. until 10 a.m. Now, we are giving you 5 opportunities to take this final exam. You can take it at the usual time, or you can take it at any of 4 other times. And all 5 of these times are listed on the sheet here. So what you're going to do is you're going to find a time that works for you, and you're going to circle it next to your name. And then you're going to write it down somewhere. Make sure that you know exactly when you're supposed to be coming in, okay? The default for us is the column that has the arrows under it. So if you don't want to have to worry about making sure you're not double booking yourself, like if you have a final exam somewhere else but you're just not sure of it yet, then go to the column that's got the arrows. That's when we're here, and you have no conflicts in terms of GCC at that time. But if you want to take it earlier in the week, you have opportunities. You don't need to commit to this today, but I'll ask you to commit by Monday if you don't have a decision today, okay? So just go ahead and find your name, circle, and that'll be that. Okay, so we'll start with the objective up here at the top. We'll go to Morgan. Oh, Morgan is not prepared. Chris. Okay, thank you. All right, let's go to Dwight. Okay, so go ahead and try that. So you're going to type in this number right here, 6022 with 20 zeros into it, and then hit enter. And then write down what your calculator says and see if your neighbor's calculator says the same thing. And you're going to do the same thing with this number with 10 zeros in the front of it. So try each of those. Okay, so on the calculator that's projected, I've got both answers up here. Your calculators might say slightly different things, but they should represent the same thing. So what we're looking at here is an example of something called, you guys know what the name of this is? Chris? That's scientific notation right there. So in science, scientists often have to deal with numbers with a lot of zeros in them. Really big numbers that have lots of zeros at the end, or really tiny numbers that are really close to the number 0 and have lots of zeros in the beginning. And you could imagine, you know, like on astronomical units, we have huge distances, huge masses, huge everything, really big numbers. But then on like the molecular level, you have really tiny masses and really tiny distances, really close to 0. And it's quite awkward to write these numbers out with all the zeros, and it's probably even more awkward to read the numbers with all the zeros, and it's really easy to miscount the number of zeros. And so we have this thing called scientific notation, which is supposed to be a compact way to get across these numbers without writing all the zeros, and that's what we're looking at here. So let's see if we can start filling in some stuff here. Okay, so the size of the number, let's fill in there. How many digits are there in this first number right here? Daniel says 24. Agree? Disagree? Okay, so 24 digits there. And then what we're going to do is write that number in scientific notation. And scientific notation is essentially what we're looking at in this first number right up here. It says 6.022. I'm going to start by writing that. 6.022. And then it says E23. Now the E stands for exponent. And if you're going to have an exponent, you need to know what the number is that's below the exponent, right? And our whole number system is based on what number? Like if I say 64, what does the 6 really mean? It's 6 tens, right? And if I said 538, what does the 5 really mean? It means 5 100s. Everything for us is based on tens, right? 10 squared is 100. 10 cubed is 1,000. So when we say E, we are talking about an exponent on the number 10. It's always on the number 10, and the exponent in this case is 23. So that right there is scientific notation. 6.022 times 10 to the 23. Now, would you guys agree it's a whole lot fewer things to write, fewer characters to write in that version of the number than in this 24-digit version of the number, right? It's a lot more compact. Okay, so let's see if we believe it. Well, you guys know when you multiply something by 10, what do you do with the decimal point? Move it over one space to the right. If you multiplied a number by 100, what would you do with the decimal point? 2 spaces to the right. Okay, we're multiplying by 10 to the 23rd. That's 23 spaces to the right. So if I move this decimal point 23 spaces to the right, well, I'm not going to write it all out, but I can move it a little bit. Let's move it 1, 2, 3 spaces there. 3 spaces to the right, which means I have how many more movements to make? 20, because we said we were moving 23 places to the right. Well, what numbers are there after that 2, which I didn't have to write? There's a bunch of zeros. You could write as many zeros as you want after a decimal point right at the end without changing the value of the number. So there's how many zeros invisible that are underneath that? 20, which is exactly right, because we said there were 20 zeros, okay? All right, so that's fine, and then we can fill in the last column here. It says the exponent on the 10 is what number in this case? Is 23. And so even though the calculator writes 6.022E23, I don't ever want to see you write E. E is a calculator ease type thing. We always write times 10 to the blank. Okay, the next one, this 0.0006742, I had it in scientific notation, so let's write that out. So what do we write first? Okay, what's the next thing after you write the kind of number part in the front? It's always a times, and it's always a 10. So built into scientific notation are those two symbols there, a times symbol and a 10, every time. And what's the exponent? Negative 11. Negative 11. Okay, we said that if we multiply by 10 to the 23rd, we move 23 places to the right. If we multiply by 10 to the negative 11, which way do you think we're moving? We're moving to the left. How many places? 11 places. So we're going to move that decimal point 11 places to the left. So I'm just going to move one place to the left to start, which means I have how many more movements left to go? 10 of them, which is exactly corresponding to the 10 invisible zeros that I didn't write in the front of the 6. Right? And so the exponent on the 10 in this case is negative 11. We didn't write this before, but the size of the number in decimal form, how many digits did we have to write out? Not counting the first 0 here. 10 zeros, 11, 12, 13, 15. 15 digits in that number. And many fewer characters when we write it in scientific notation. Okay, so how do we know how to write a number in scientific notation? The calculator did it for us and we just copied it. Okay, so the common theme here in both of these cases is that there were how many numbers to the left of the decimal point when we write this in scientific notation? How many numbers are to the left of the decimal point? Just one. How many numbers are to the left of the decimal point? Just one. That's part of the definition of scientific notation. You need to write the number so that there's exactly one digit to the left of the decimal point. For example, I could take this guy and write it as 60.22 times 10 to the 22nd power, which means move the decimal point how many places to the right? 22, which is going to get me there. It's equivalent to both of the numbers that are up above. But it is not in scientific notation because there are how many digits to the left of the decimal point? 2, and we're only allowed to have 1. Okay, so scientific notation means there's exactly 1 digit to the left of the decimal point. I guess I should highlight the word 1 non-zero digit. You don't get to put an extra 0 in the front. It's got to be 1 non-zero digit. Okay, so number 2, we'll go to Lily. The bottom here. All right, I don't expect a lot of folks recognize the second number, but some of you might have seen this first number before. What is it called? It is, but it's a famous number. If you've taken a chemistry class, you might have seen this magical constant before. I don't know if I'm going to spell it right, but I'll try. Anybody heard of that before? Avogadros number? It's this constant in chemistry. Apparently it's important. I don't know what it's counting. It's like the number of hydrogen atoms in a mole of something. I don't know what a mole is, but apparently this guy found this number, and it's an important number for us. So that's Avogadros number. This other guy right here is something called the gravitational constant. And if you want to find out more about that number, you can look it up. And let's go to the next page. And we'll go up here to the top. Kyle? Okay, with your neighbors, can you guys fill in the 4 blanks? I'm asking you to go in the 2 different directions, depending on the row. All right, how are we doing on these numbers? Can you guys check my work? We agree or disagree with the numbers on the board? Questions on any of these 4? Ask now if there's any confusion. Okay, so for the 2.03 times 10 to the 6th, what we need to do is take that decimal point, and first of all, we're moving it left or right? It's moving to the right because that 6 is a positive number. So we got to move it 6 places to the right. So the first 2 moves to the right, 1, 2, get me to the end of the number that's written, which means the remaining moves to the right are going to involve tacking on zeros that aren't there. So again, we were moving 6 places to the right. How many have we already moved to just get the end of the number? We just moved 2 places. We're supposed to go 6. We've already moved 2. How many more do we have to go? We need to go 4 more. And that's the 4 invisible zeros you need to bring in. Questions on any of the other numbers? Okay, so let's just kind of summarize here about the basic ideas between big numbers and small numbers. Big numbers, like for example here and here. What was true about the exponent for both of those big numbers? It was positive. Big numbers, positive exponent. That might be worth writing down. Big numbers, positive exponent. And then we had two numbers that were very close to 0. And what kind of exponent did we have? Negative. Close to 0, negative exponent. Close to 0, negative exponent. Okay, so this whole scientific notation thing is just a technique, and it's easy once you have the technique, but until you have it, it might just look quite mysterious. So I'll ask again, are there any questions on any of those 4 numbers? Okay, let's go to Sarah for number 4. Oh, sorry, the others. You're Sadie. That's Sarah. Okay, so imagine the length of this particular building. Is that a big number or a number close to 0? It's big. I mean, big is relative, but it's definitely not close to 0 in terms of how many feet it is. So it's big, probably hundreds. So big numbers, what kind of exponents do they have? Positive, so that's what we put in the blank here. Positive. Big number, positive exponent. Number close to 0, negative exponent. All right, let's go to Sadie for 5. Okay, so here's a calculation for us to do without the calculator. 36 times 10 to the negative 4 divided by 3 times 10 squared. All right, so there are a couple of different ways to handle this, but I'll give you what I think is the most straightforward way. My first thing that I'd like to do is make it so I have no negative exponents. We've already seen negative exponents a couple of times this semester. Negative exponents indicate movement. Okay, the 36, does it have any reason to move? No, so the 36 stays. 10 to the negative 4, does it have any reason to move? Yes. So where do we move it? The bottom. So downstairs, I'm going to put a 10 to the positive 4. Right? Just move that negative exponent down to the bottom. Does the 3 have any reason to move? No, so we'll keep the 3. I'll put a dot. You can use an X if you want. Does the 10 squared have any reason to move? No. Okay. Next thing we're going to do is divide, but only the ones that kind of go together. You can see there are 10s, and then there are numbers that are not 10s. So all I'm going to do is take care of this thing separate from the 10s. It's just kind of grouping. 36 divided by 3 is 12. So there's a 12 upstairs. 36 divided by 3, right? The bigger number is upstairs, so that's where the 12 is going to go. And then we have a collection of 10s. 10 to the 4th means 10, 10, 10, 10. And then another 10 squared. So how many 10s do we have down there? We have 6. So downstairs is 10 to the 6th. Questions on either of those parts? 12 or 10 to the 6th? Okay, it might be tempting to start reducing the 12 and the 10, and we cannot do that. The 12 is freely available for reducing, but the 10 is blocked in by that power, so we can't go into the 10, right? But what we need to do is one extra step, because it says write it in scientific notation. So, in order to write it in scientific notation, I can't have a 10 downstairs, I need to have a 10 upstairs. So I need to move this 10 back up to the top. So how do you move this 10 to the 6th upstairs? We'll make it 10 to the negative 6. So this is 12 times 10 to the negative 6. We know we can move an exponent thing and just change the sign. It was positive 6, now it's negative 6. Okay, super. So that's scientific notation, right? It's not. Why not? Yeah, if you put in the decimal point just to really see it, it's got 2 digits before that decimal point, and that's not okay. right? Scientific notation is only allowed to have one digit in front of that decimal point. So we need to do even more work. One last step here. I need to move that decimal point which way? I need to move it to the left because I need to have only one digit to the left of that decimal point. So it needs to be 1.2 times 10 to the, and then we got to fill in. Definitely need to move this guy one place to the left. Okay. It seems to me there are two reasonable answers for what the new exponent is going to be. It used to be -6. We moved one place to the left. What's one reasonable new power? -7 is quite reasonable. What's the other reasonable new power? -5. We just have to decide. Like, we're clearly moving that -6 one direction or the other. We just got to figure out which way to go. So here's how I remember. Did you make that 12 bigger or smaller? You made it smaller, right? Well, in order to pay for that, like, you can't change the number. You got to make the exponent bigger. We made the number smaller. 12 became 1.2. Definitely got smaller. In order to balance the scales, we got to make the exponent bigger. All right, now it's a negative exponent, so we got to be really careful what we mean by bigger. -5 or -7, which is the one that's bigger than -6? -5 is bigger, right? Like 7 sounds bigger, but it's going the wrong way on the number line. So this should be to the -5. And so I'll just write in here kind of roughly the thing that we just said. If you make the number smaller, that's what we did. Make the exponent bigger. It's not really well defined. What's that? And then vice versa. So I won't write the other sentence. Maybe I'll just write the two words. If you make the number bigger, make the exponent smaller. And when I say the number, I hope it's clear I'm talking about the part that's in the front of the 10. It was 12 in this case. Questions on that? Just think about balancing a scale. If you make one part of the number bigger, you got to pay for it, make the other one smaller, and vice versa. Okay, there is a table for your reference. You can check it out later on, but go ahead and start the classwork and see how far you can get.